with some review of where we left off. So we were looking at different probe and coil types. And so we talked about absolute versus differential versus reflection. And then finally, hybrid probes. How would you describe these? So can someone describe what's an absolute probe? Remember? Yeah. Typically a single coil. What's that coil doing? Generating and sensing. Good. You're looking at your notes. Okay. Good to do. Okay. How about a differential style setup? What do we got going on there? How many coils are there? I'll start with the softball portion of it. At least how many coils? Morgan's got 2 fingers up. So we got 2 coils. And how are those operating? What's the theory behind that? Or what's the design of that? I think you're getting a little bit ahead. You're looking at a reflection style. So, okay, so now we said reflection also is two types, and we've got a transmit and a receive. So that being reflection, what is differential then? Differential, they're both a driver and a pickup. We're running that current generating or that field generating current through both coils, and then we're picking up that signal from both coils. And we're comparing that change in inductive reactance between the 2 coils. And so then finally we talked reflection, and Alex mentioned that, is we have at least 2 coils. Anyone miss the sheet? We have at least 2 coils, and the difference there is what's happening now, Alex? So one's sending out, one's a pickup. I'll hand those out in a minute, Shadi. You can leave those there. What are the names of those 2? What do we typically call? What's the coil that sends out the signal? That's our driver, okay? And the receiving coil is the pickup coil, okay? We looked at some of the different ways, kind of the indications, and as we go over different crack sizes, you get a bigger indication. If we know what these cracks are in a standard, we can get an estimate of the flaw size based on what we see on our screen. Okay. So looking at this screen, what is the line going from B to A, or this line across the bottom? What's that called? What generated that line? That was, what's that? Runaway? Okay. So what are you doing with the probe? What are you doing with your hand? You're picking it up or setting it down. That's your lift-off indication. Okay, you're lifting the probe off or setting it down. And then the ones going to C, D, and E, or the 3 that are on the right here above, right, are your 3 flaw indications that are showing, this crack standard has 3 flaws. So we talked about some of the advantages and disadvantages, and that differential probes are more sensitive to immediate changes, but they're not going to pick up gradual as much. And with reflection probes, we can find very, very small flaws because we can tailor our driver and our pickup coil to their specific purpose. One is better at creating those fields. The other one is better at sensing the fields. You don't get that what's called skin effect as much because the 2 coils aren't being, or the pickup coil isn't being affected by the current being run through it. And hybrid is kind of any combination of these. So we looked at a few different wiring diagrams for them. And so we had absolute, known as they call it a single coil probe, an absolute probe. Here were the reflection probes showing the driver to one side, one set of coils, the pickup on the opposite set of coils. And they called it a bridge or a differential probe where we're driving and receiving a signal from both coils there. And then we looked at array probes, which are kind of a hybrid combo of this. We saw the video for some of these flexible type array probes where they can be a bunch of coils arranged in all kinds of different arrangements. With any of these probes now, getting into kind of the newer material, we can have probes that are either shielded or loaded. And these are to increase the capability or to make the probe act in a certain way to help better find indications of a certain type. So probe shielding is kind of, as the name implies, goes around the outside of the coil. Okay? It's some type of material around the outside of the coil in order to prevent interference. And so the magnetic field, if you have objects or features that are close to the coil, so in addition to what's directly in front of the face of the coil or below it, features that are kind of surrounding it have the potential to affect the inductive reactance of that coil as well. So I'm going to grab a couple markers and just kind of draw an example of what I'm talking about here. So say we had a part that kind of had a step geometry like this. Okay? And when we brought our coil over the part, and I'm just going to draw a single absolute coil because that's the kind of easiest to draw. We've got our coil like this, right? The majority of the signal we're going to see is going to be in this area directly below it, right? But there is going to be some effect. There is potential, there is going to be a little bit of kind of field on each side as well. So as we move that probe or that coil close to the step right here, we might start to get some effect from the metal in this step. So not only will we be picking up and getting a change in inductive reactance because of this surface below, but now that field off to the side is going to interact with that metal or material that's creating the step. And so if we put some kind of a barrier around it, we're going to try to prevent these magnetic fields from forming on either side. Okay? So magnetic shielding, there's two types. Magnetic shielding is some kind of a ferromagnetic material, and that is going to help prevent this by focusing the magnetic field down or in front of the coil in the direction that we want to perform our inspection. It doesn't necessarily prevent this from happening, but it kind of shifts this additional energy from being out to the side. It kind of shifts it to be more pointed in front of the coil. Okay? Eddy current shielding is a non-magnetic but a highly conductive material, so like an aluminum or even like copper, typically like a copper or a brass or a bronze. That is, what will happen is that will get eddy currents forming in itself. But it creates that skin effect around the outside of the probe, which is going to prevent those eddy currents from being able to continue out into that step material, into that material around the outside. Okay? So the magnetic shielding, again, ferromagnetic material is going to kind of force this magnetic field more down in front of the face of the coil, whereas a eddy current shielding, typically copper or aluminum, around the outside of the probe, it's going to create kind of a skin or a Faraday cage, if you're familiar with what a Faraday cage looks like. And so that's going to limit the effects of, features that are not in that area that we're trying to investigate or trying to get a signal from. Okay. Another way we can affect the kind of how the coil interacts with our object is we can load the coil. We can do what's called probe loading. And in that case is, the coil typically has to be wound around something. Now they can be wound around air in the sense that there's some kind of a hollow tube that they get wound around. Or you can wind them around some kind of a more solid material that can help to concentrate the magnetic field as well. And so if we wind it around a ferrite core, a ferromagnetic material, rather than either like a plastic or just a hollow, air-filled space, that also is going to help concentrate the magnetic field kind of in front of the coil, in the direction that we want that coil to be looking, so to speak. So it concentrates those eddy currents, that magnetic field, kind of right in the center of the coil. And so it is going to make it more sensitive because it's going to generate stronger fields in the area that we're performing our investigation. It's also going to help too to minimize some of the effect, some of that edge effect. But Again, more for sensitivity increase and to reduce the effects of wobble or liftoff and prevent those false indications. Our different types, we've talked about this in earlier lectures, but just a few kind of reminders on what kind of indications you might see. So the non-relevant indications and limitations of this, the test coil is going to interact with our test piece. I mean, that's how we get our indication. During normal use, a liftoff would be considered a false indication, an accidental liftoff. When we're calibrating the device, we typically are going to intentionally perform a liftoff on our calibration standard so that we know what it looks like, so we can recognize it if it were to happen accidentally during the process of performing our inspection. Right? By looking at it on that standard, we would know when we go to, say we have a skin standard and we're going to go check rivet lines on an aircraft skin, and we want to make sure that if we don't want to confuse an accidental liftoff of the probe with what would be a relevant indication, a crack or a corrosion indication. So we're going to intentionally do that as part of the setup process to see what that looks like. The other thing we're going to do is we're going to look at edge effect, and we're going to see what that looks like before we start working with the part. Now, the diagrams I had up there didn't have edge effect on them. But essentially what happens with edge effect, let's use this, is that as we bring our coil near the edge of a part, so as we start to bring our coil over here, and we move it off that edge, there's going to be less and less metal or less and less material in front of the face of the coil. And that is going to change the inductive reactance of the coil. And so we want to see what happens. So again, if we're looking at a screen, right, we've got the tester in one hand, we've got our probe in the other hand, typically you're going to have to be watching the screen while you're moving this probe around. It takes a kind of a left brain, right brain bit of skill to be able to operate this. But you're looking at the screen and you start to get near the edge, at first it'll look like a crack indication. We want to make sure we don't accidentally confuse it with a crack or a flaw indication. What I mean by that is if I draw our impedance plane diagram, which is the screen, we've got our screen here, and I draw our indications, and I'll use that absolute probe example again. So we have our liftoff that comes over to our origin point here. We've tested our liftoff. We're also going to bring our probe near the edge of our test standard. And what we'll see is something that looks a lot like this. So you can see it'll start like, can you see that okay? Or is red a really bad color? Blue any better? That's about what I got. So back to our origin point, we'll see that indication. If we had crack indications, here would be our small, medium, right? We've tested different cracks, different known cracks. But you can see an edge effect would start to look like a very large crack, but it would keep going and going. And then we would reach the point where that probe essentially slid off the side of the part. And when that happens, it's going to shoot off the side of the screen and kind of work like a liftoff indication. Okay? So we want to see what that looks like as well, so that, again, we know what does it look like when our probe meets or breaks the surface? What does it look like if we start to run off the edge? And then as we go across our part, or our test standard, what do various crack sizes look like? Now this is just that one form. Remember, depending on the type of probe you're using, you may get slightly different, you'll get some different kinds of indications, more of the bow tie shape or kind of the more looped shapes. So as part of your setup, you want to see what that looks like for your probe, for the material you're testing, for the type of indications that you expect to find. And that's why we have to have some kind of a standard to compare against when we're setting up our testing equipment. The third thing here is skin effect, and this doesn't really create much of a indication per se. But what this is remember when we create those eddy currents, when we looked at the strength of the field, where was it concentrated? Where is the field the strongest? When we looked at like depth of penetration, that kind of thing. It's near the surface, right? And those eddy currents are going to generate their own magnetic field. Magnetic fields can almost act, they can block you from seeing further into a part. So, the eddy currents and the magnetic field they generate near the surface is going to prevent you from being able to see too far into the part. We looked at what affects depth of penetration, frequency of the probe, conductivity of the material, how easy it is to magnetize the material, right? And the only one we can really control is the frequency, right? The material's conductivity is fixed by the material. Its ability to be magnetized or not be magnetized is fixed by the material. So who remembers, if we want to overcome skin effect, how do we get a greater depth of penetration? We go, what's that? I think I heard it in a couple places. A lower frequency. Lower frequency, remember, is going to give us a greater depth of penetration. It's not going to form these surface eddy currents as strong. It's going to be able to create those eddy currents deeper in the part. Okay? To be able to look for subsurface flaws, or in the case of like sheet metal, backside flaws for corrosion and that kind of thing. Yeah. Well, so what's the disadvantage to lowering the frequency? What does lowering the frequency do? It gives us greater depth of penetration, but there's a trade-off. What's the trade-off? The sensitivity goes down. So if you are setting your frequency in such a way that the depth of penetration is so deep that it's beyond where you would be looking for flaws, you're reducing the sensitivity in the area that you are interested in. So that's where that balance comes in. Okay? And that's where like the multi-frequency probes come in. Where they can run, it can kind of swap back and forth between a high frequency and a low frequency. Or like that array probe that we saw the video of, where it would run kind of different combinations of coils, different size coils, different frequencies, and it could do, it could map front side features and back side features and everything in between. So the more, those more sophisticated probes and testers, can kind of overcome some of those effects. Or with a simpler tester like we have, you may have to, if you're looking for both front side cracks, back side corrosion, you may have to set it up for those surface cracks and use a small surface probe. And then if you're also concerned about corrosion, in a lap splice or something, you may have to reset everything on your tester, use a larger, lower frequency probe and go back over the same area, right? So you can do it, it just takes longer, more effort. Whereas if you have a multi-frequency device that can do that all at once, multiple coil sizes, can cycle the different frequencies, you may be able to do the inspection faster in a single pass, that kind of thing. So we talked about the test standards. Here's just some standards. Here's what we're going to be using in class. So here's that block with the various sizes, 8, 20, and 40 thousandths right here, different depth cracks. We have a block like this that has a radius, and there's a little crack shown down in the radius. You're going to be looking at cracks in the radius. Now you want to be going perpendicular to your cracks. So something like this, your probe, you're going to be moving kind of this direction to try to find that crack. If the crack is running perpendicular, this block, you want to be going left to right. Okay? There can also be blocks that have holes in them, and typically what they'll have is 2 holes of the same size. One will have a crack in it, a simulated crack. One will not. So you can compare what kind of indications you get with one or the other. When you're doing bolt holes where you're putting your probe down in there, you can't really get a lift-off indication because the only way to remove that probe is to pull it up and out. So most of the time you kind of get a combined edge effect as you get near the top of the hole, and then kind of that liftoff. You can't get just a dedicated liftoff if you're using a bolt hole probe that goes down inside of one of those. You can also do ones, we're not doing this, but ones where they have different kinds of threads in there, damaged threads, cross threading. You can actually pick up those differences with certain types of probes and certain types of inspections. So just a summary of the equipment. Back in the day, we had analog meters. We didn't even get a readout like this. All we had was something that measured the inductive reactance of the coil, and you looked for a deflection of a needle. Those are long gone. I haven't seen one in the industry. You guys see one? Most now are going to use the impedance plane display like we're showing here, and those are all digital-based, digital circuitry. And more what you're seeing is the imaging type, the C-scan type. So this is, that was the one that was shown in the video, where they were able to map the contours, the corrosion, the pitting, the holes, the cracks that were in that kind of sample plate that they ran that array probe across, and be able to create a 3D pictorial view of it. In these, there's some kind of a power supply and a frequency generator. This relies on changing magnetic fields. So it has to be an AC current that we're running through our coil. So we have to have the frequency generator. That's where we can control what the frequency is of our coil, which can control depth of penetration and can control sensitivity. And then you've got all kinds of different impedance measurement, gates, alarms, filters, and then your various probes, probe arrays, bobbin-style probes, and circling probes that we talked about earlier when we looked at all different probe shapes. So you put that all together, and you get your eddy current tester. And in lab, we go through today. Those of you that had lab on Tuesday, we went through the setup and basic operation in lab on Tuesday. The rest of you, we're going to go through the setup and basic operation today. I'll do a demo of that. And then I've got a bunch of videos that you can kind of watch. When I would go home while you're working on this, I can put these on. I'll show some of them too while you're working on your research project. But I'm not going to dedicate time to them. But there's some interesting stuff there. Things like wheel inspection. I've got a comparison of manual versus automatic using some of those contour probes, or even some of these. There is non-contact testing. We talked about the fact that you don't always have to have the probe in direct contact. It just has to be in close vicinity. That's how that aircraft wheel inspection works. So.